This is kind of a special conference to me and a special opportunity to speak because about 4 years ago when I first came on as CEO of Made in Space, Pat was kind enough to ask me to come and speak. And it was like the very last keynote of the very last day. And I was quite nervous and didn't do the best of jobs, so hopefully this will be better than last time. So just as a brief overview, Made in Space is an in-space manufacturing company. We're known for being the first company to ever successfully manufacture functional objects off the face of the planet with a 3D printer on the International Space Station in 2014. Since then, we've really expanded the portfolio of in-space manufacturing capabilities on orbit. We launched a second generation machine in 2016. We launched a Z-blade manufacturing device a couple of years ago. Have operated that several times now, and are really expanding our capabilities as humans in doing in-space manufacturing and assembly in space. So why does this matter? In-space manufacturing matters, simply put, because it gives us a reason to go and stay in space. And that's really core to the sort of fundamental vision that we have at Made in Space, and I think many companies that are represented here today have, which is that we want to see people sustainably live and work in space. I always kind of joke that I want to see people with boring jobs in space, because that's a great signal that we've successfully expanded our economic influence into this great frontier. And I also really think that in-space manufacturing, manufacturing in space more generally, really leverages, stands on the shoulders of giants of the successes of other sectors within the space community. We live in an era where, reliable, reusable rockets are commonplace, right? I have a colleague of mine who has 2 small children, and those children will not get out of bed to watch a launch unless there is also a return associated with it, which is, just totally like a really weird, thing to think about. We live in an era of mature small sats, right? That are essentially built on the successes and the evolution that we've seen in electronics, driven by things like laptops and smartphones. We even live in a world now where there are like multiple, legitimate, technically hard-nosed companies that want to build commercial space stations. They want to build the successors to the International Space Station. And all of these things both enable us to go and stay as a species, and will be leveraged, and the potentials of them will be unlocked by the synergy with in-space manufacturing. If we think about our friends at Axiom Space or Bigelow Aerospace, these commercial space station providers, what's the one thing that they really want? They really want creditworthy tenants who will be there, be able to buy a portion of their module or lease a portion of their module and operate. And in order to do that, we need we need to be doing things that are profitable in space. Tourism is really amazing, and I believe will be an important part of the commercial low Earth orbit ecosystem. But manufacturing in space, processing of materials in the microgravity environment, that because they're processed there, they have new and interesting properties and are valuable and are profitable to launch, do some process in space and then return down to Earth to sell into our global markets. That really is, to me, the anchor tenant for commercial space station operations. I'm not going to talk too much about that today, but that is an area that we and many other companies are pushing really hard on, right? Like we've built and launched a device to manufacture Z-line optical fiber, which has a 10 to 100 times better signal loss than traditional silica fiber. We've done that. We've operated the device several times on the ISS. We're building a second generation of that device to launch, in the coming year or so. There are other companies that are working on things like bioprinting that might enable us to make, heart valves one day in space, and other things like that. There's also companies working on, high throughput research to do in space. Taking what we might do for drug discovery on the ground, doing that in space, and adding to our, our collective knowledge and consciousness that way. Another really interesting area, though, about in-space manufacturing is manufacturing and assembly of satellites in space. That every satellite we've ever sent to space, we've done it the exact same way, right? We fold it up, we fit it in the top of a rocket, we blast that rocket into space, and subjecting our payload to a really high G environment. It gets to space, it unfurls itself, and then it operates for 5 or 10 or 15 or more years in this this very mechanically benign environment. And that's really, really cool. That's that rocket ride is the reason that my colleagues' kids get out of bed in the morning to see, as long as there's a return. But it's inefficient, right? Because we design our satellites to survive that rocket, rather than optimizing our asset to function in its operational environment, which is fundamentally appealing to us as scientists and engineers, and even humble recovering lawyers. And but in order to actually do that, that's where in-space manufacturing and assembly comes in. Is that if we launch raw material and a hardened manufacturing platform to space with our satellite to manufacture things like large antennas or large solar arrays, we can make those really delicate things not have to survive the launch loads, and we can make them in an efficient and an optimized way for the space environment. Now, and this is really important, because what I think that one of the things that we've seen over the last decade with the sort of the evolution of the launch industry is that we've gotten really good at, we've gotten more efficient at launch. The price has gone down a lot, but we haven't seen necessarily a similar, we haven't seen a similar spike in new launches. The pie of launch has not doubled when the price dropped in half. It maybe expanded a little bit, so we're just kind of slicing this pie thinner and thinner. But things like in-space manufacturing of goods and things like manufacturing satellites in a way that's optimized for space, I believe will actually, will expand the pie. We'll expand our pie of the pie of operations, we'll expand the pie of launch. So maybe just to articulate this a little bit more. Historically, we live in this world where maybe a Falcon 9 costs $60 million or so, and we put a satellite on top of that costs like hundreds of millions of dollars, and it produces kilowatts of power to do its scientific, to do its mission. We'll get into this in a little bit detail in a moment, but in-space manufacturing and assembly, on-orbit manufacturing, potentially allows me to launch a satellite that that has a mass that's a fraction of the satellite that you put on the Falcon 9. But provide it the same class of power. Give it kilowatts of power, maybe even 10 or more kilowatts of power, but on a small satellite bus. So now we're launching a satellite that maybe costs tens of millions instead of hundreds of millions, and we're putting on a rocket or putting on a ride share that costs $5 or $10 million rather than $60 or $100 million. So I think this is a really important shift, because right now what we're doing is taking a $100 or $200 million asset and we gave it a discount. We put it on a $60 million rocket. But what we have an opportunity to do is take that same capability and lower that price even further, and to tens of millions, to knock off a zero, and also put that on a rocket itself that's in a similar kind of class of cost. And that kind of savings really has the potential to expand the pie in terms of the different kinds of operations that we can do in space with satellites. And in-space manufacturing and assembly, I really think has, it opens up an incredible future where, from low Earth orbit out to deep space, as we can kind of see in this picture. In low Earth orbit, we have satellites that, if we're enabling things within space manufacturing and assembly, look really different than the satellites of today, right? You look at some of these concept images, and you just kind of like try to think about how we might do this in a traditional launch sense, and it becomes very, very difficult, as well as doing things like manufacturing material and microgravity. So how do we actually get here? What are the actual, what progress is actually being made on this? So at Made in Space, we think there are 5 key steps, 5 key pieces to being able to do in-space manufacturing and assembly. The first piece is that you have to be able to manufacture in microgravity. This is something that we've been doing, as I mentioned, since 2014. That's a picture of Commander Butch Wilmore on the International Space Station holding a fully functioning ratchet that we manufactured in one print in response to a need that he had on the space station about 5 years ago. The next is you need to be able to do this manufacturing in the vacuum of space, in the thermal and vacuum conditions that you're going to experience in space. We also care about things like radiation. The third piece is really, really important because typically when you think about manufacturing anything, you kind of, and especially with 3D printing, you kind of think of a big box that chunks out things that are smaller than itself. And that's really cool, that's useful on the ground where we have lots of space and mass constraints are not really a huge factor. But when we go to space, we're probably not gonna launch like a 50-meter 3D printer space and chunk out like 20-meter reflectors. We wanna launch something really small that can make really large things. So we've developed a technology that we call ESAM, which is extended structure additive manufacturing, that can do just that. From a small box, it can manufacture arbitrarily large structures. In fact, we have a structure in our office in California that is 37.7 meters long. It's longer than the solar wings, than a solar wing on the International Space Station. And the reason it's that specific length isn't because there's some geeky leet speak thing going on there. It's actually because our building was that long. We ran out of space to make that to keep going. And of course, the next piece here is that it's not good enough just to be able to make things in space. We need to integrate those and make them useful. So that's where robotic assembly comes into play. There's lots of really good folks that are really talented with robotic assembly. We put a heavy emphasis on not only being able to do it, but being able to do it in an autonomous, repeatable, and recoverable fashion. Because things don't always go the way you want them to go exactly, and you want your system to have a little bit of smarts to say, hey, I've encountered a problem, I'm gonna stop, and I'm gonna call home, and I'm gonna say, what do you want me to do? Or, and also suggest a method for potentially recovering the operation. And finally, you need to be able to verify for yourself and for your customer that what you've done, that you did what you said you were gonna do, which is where inspection and verification comes into play. So putting all these pieces together, we've been working on these pieces for several years now, and we put these pieces all together into a kind of platform, a general manufacturing and assembly technology that we call Archinaut. We specifically chose to make Archinaut and to have the sort of design language and thoughts behind it be general rather than specific, because we wanted this kind of paradigm to minimize the NRE between missions. That the same robotic system that assembles a solar array could be used to assemble a reflector, or could be used to assemble a radiator. That's also beneficial because it means that we're getting, the heritage that we're getting on these manufacturing assembly subsystems is increasing with every mission. The changes are minimal between missions, compared to something that might be more specific, like a point solution for building like a really amazing L-band reflector. While that may be a little bit more optimized, you lose the potential benefit of having a more generalized tool in that regime. So, as I mentioned, we've been operating on the International Space Station for a couple of years now. We were fortunate enough to receive a tipping point contract from NASA a couple of years ago to start burning down the technical risk with these programs, culminating in a series of TVAC tests to first show the ability to do in a TVAC to manufacture extended structures, and then to about a year later do robotic manufacturing and assembly in that TVAC. But we all know that we're in like a relatively conservative industry, right? And we're all willing to fly anything as long as it's flown once before. So how do we get over that hump? Well, the way we get over that hump is again, fortunately, partnering with NASA via public-private partnership to actually design, build, launch, and operate the world's first satellite that will manufacture and assemble portions of itself. And that satellite is this guy right here, Archinaut 1. It's a very Silicon Valley name, Archinaut 1. So this is a definitive demonstration of the ability to do manufacturing and assembly in the space environment. Right now, this is looking to fly in 2022. It's a small satellite, weighs about 200 kilograms. And you'll see on that small satellite, we have two very, very large solar arrays. And you'll see in the middle there these two sparse-looking spars. Those are actually manufactured on orbit. We'll stow on the interior of the satellite assemblies that contain these rollable solar arrays. And when we get on orbit, we'll robotically remove those, put together that assembly, and position it so that we can manufacture one of those long spars, creating a solar array that's about 10 meters long and about a meter wide. And then we'll flip all that around and do that same process going the other way. So once this is all manufactured on orbit, we'll get about 20 square meters of surface area on orbit, which is substantially more surface area than any small satellite has deployed in the past. And on this mission, if you were to use kind of state-of-the-art solar cells, like things that exist right now, we could generate 5 to 8 kilowatts of power. Whereas the state-of-the-art, the sort of flown, demonstrated state-of-the-art on small satellites is maybe like 1 kilowatt of power. So we're talking like 5 to 8 times the state-of-the-art being demonstrated here. And that's a really, that demonstration is fundamentally, shows that we can fundamentally do this in space. But it's not just about building, it's not just about providing big power for small satellites. This is a generalized capability. That same device that can manufacture those spars can be used to manufacture antennas. The same robotic arm that's going to assemble those solar array boxes can be used to put together, to put together radiators, to put together big reflectors. And this is really about eliminating two constraints that we have on spacecraft today: volume, volume and mass. That for every spacecraft that we send up, because the mass of those spars that we're going to manufacture on orbit is significantly lower than comparable deployables that you'd buy off the shelf today. All right, well, there we go. So to kind of close out on a couple of specific near-term examples of this, Archinaut 1 is going to definitively demonstrate this technology, but it's also a platform that provides a significant amount of payload space on the front of it. That we're flying a payload on it for the first mission. There's a high power payload to use the amount of energy that spacecraft provides. But this same platform, it almost serves as a next generation satellite bus for small sats, where you can say, hey, do you need a lot more power because your sensor, because we have these high power sensors now that we're flying on large satellites. Maybe we want to fly those on smaller satellites so that we can, take advantage of lower launch costs to get a similar capability to space. That's enabled by Archinaut. To show, again, to illustrate like the sort of broad-based technology that exists here, the broad-based enabling technology that exists here, this is a picture of a ground-based mock-up of a structurally interconnected interferometer spacecraft that we call Optimast SCI. So this actually manufactures two about 10 to 20 meter long booms to do interferometry in low Earth orbit to spot near-Earth asteroids. The same ESAM that's flying on Archinaut 1 lives inside of this and enables this kind of mission. Similarly, really large reflectors like we see here in these pictures, 10 meters plus, also enabled by the ability to manufacture and assemble with Archinaut. Going on a little further, it's really exciting that MEV-1 is launched. Our first commercial satellite servicing mission is now on its way to GEO. And that mission, but satellite servicing really could be enabled by including manufacturing assembly on those assets. So not just talking about refueling or shaking a solar array so that it pops out, but augmenting and adding structure and adding sensors to those assets to extend their lives, to get more to a paradigm where satellites aren't sort of fire and forget, but the satellites themselves are reusable and repairable and extensible. So in closing, we're really like the early stages of in-space manufacturing assembly, but I I truly believe that this technology will be as paradigm shifting and revolutionary for satellites as reusability was for rockets. And thank you so much for your time.
Thank you, Andrew.
Yep.
We have a few questions from the floor. First of all, we need to get a copy of your charts without the proprietary markings on them, because we're going to publish all the charts.
Sure.
And we don't want to have them on our website with your
Sure.
proprietary. That would, the lawyers get nervous about that kind of thing. So number one question people have asked, explain the cost better when your manufacturing material has to be shipped to space, which is a costly supply chain.
Yeah, that's a great question. So the near-term cost benefit is around sort of dollars per capability, right? Like the ability, delivering 5 to 8 kilowatts of power on a small sat is perhaps achievable with deployable technologies, but it's really, really, really expensive to do that engineering. This is a much simpler approach, and you do get additional mass savings because the structures that we manufacture on orbit are generally significantly lighter than the deployable structure that you'd have to send. So there's 2 vectors there that provide cost savings.
Okay. Well, to follow up on that, what are the sources of the raw material for the Archinaut construction?
Yeah. So in the beginning, the raw material we brought with the satellite. So Archinaut 1 will contain feedstock spools within it that will be launched with it, and then we'll do the manufacturing with that material.
Okay, with space debris becoming a bigger issue, would you work toward not so much biodegradable but space-degradable materials?
That's an interesting question. That's an interesting question and worth like some advanced concepts exploration. I think that in the more immediate term, we're more focused on complying with with the sort of good neighbor policies of having your spacecraft last below a certain number of years in low Earth orbit.
Good. Okay. Will you do you plan to manufacture medicines in space? If so, who would regulate that manufacturing?
Oh, that's a good question. Certainly, that's something we've looked at. I think, in particular, for long-duration human spaceflight missions, those sorts of approaches are important. I think the same regulatory structures that exist for human spaceflight right now would be applicable.
Okay. The most popular question today is one that my father would tell me is a rude question, but I will ask it anyway. Who is your biggest customer?
Currently, our biggest customer is NASA.
Okay. And second like that?
What happens when you win
Yes.
the first satellite we've ever had?
When will Made in Space make money?
So we've been profitable and growing every year that we've existed. We do not, for a very, very long time, we did not have any outside investors, and we've actually doubled in size about every 18 months to 2 years.
Good. So a couple of questions regarding materials. What materials are you manufacturing that can handle the thermal and radiation environment of low Earth orbit?
It's a really good question. So, and the subject of a lot of research that we've done over the past several years. So, one material that we've demonstrated on the space station is a polyethylamide polycarbonate composite called Ultim. That's a polymer that we manufacture in pretty routinely. It's actually flown on some Air Force birds as well as a lot of MISSE experiments, and it holds up well in the vacuum as well as to the radiation environment.
Is that what you use to print antennas with?
So antennas require a certain amount of metallization or some conducting thing. There are a couple of different. So that material is something we could use as part of an antenna. Yeah.
Okay. How do you validate the structural integrity of your manufactured structures on orbit? That's
a good question. So the first way that we'll do it is, there's a lot of manufacturing on the ground, and the goal is for the manufacturing equipment to work the same on the ground as it does in space. We've validated that approach on the International Space Station. The printers that we have on the space station operate like the ones when they're on the ground, and we do comparisons there and haven't found significant differences.
Super. Could this technology be useful for making robotic landers in space for missions to the moon and Mars?
Yes.
Softball question, right? Have you attempted 3D printing of human tissue for medical purposes?
We have some internal research and development efforts around bioprinting. Good. I'll just leave it at that.
Good. Do you see your approach as being exposed to cybersecurity concerns?
That's, I think, a concern with any electromechanical device in the world or in human dominion. So yes, that's a concern.
Okay. How do you manage heat dissipation when printing the larger structures in space over an extended period of time?
Yeah, no, it's an interesting problem because you can kind of look at that wing and say, well, you're creating this like cold or hot sink as you're manufacturing more and more. So there are, within the manufacturing volume itself, we put a lot of effort into keeping the thermal environment there within a very narrow band.
Okay. Have you considered using additive manufacturing on orbit for deorbiting purposes for the end of life for satellites?
Yeah, we have looked at that on a couple of different occasions, for manufacturing things like drag sails, for instance.
Wow, great. Let's see, can you restock with the raw materials after the initial stock of build materials is used up?
Yeah, so that's one of the things that's really interesting about sort of Archinaut-infused assets, right? Is you have this residual manufacturing and manipulation capability that if you resupply that or restock that, you could have it reconfigure itself on orbit. So that's absolutely something that we build in.
Super. Here's a very popular question, and not necessarily both in this session, but it comes up every time. Do you have any internships or scholarship programs for students?
Yes.
Okay. How do you apply? I'll just head off.
Right. So for the summer, we're a member of Brooke Owens. We're a member of Matthew Izakowicz, and then our general approach for our general solicitation for summer interns turns on like in December and in the December-January timeframe. We also are interested in co-ops throughout the academic year.
So you have a web page or something?
Yeah. You can go to mainspace.us/careers and find the information there.
Good. Who do you consider to be your biggest competitor?
That's a good question. This is an area that increasingly folks that are really, really capable and much larger than us, and folks that are also, kind of some, that are smaller than us care a lot about. So former Orbital ATK, we have a lot of synergy with them in this area. I guess it's Maxar now with SSL. They're very focused on assembly in space. Those are two companies that we sometimes work closely with, and sometimes we, are kind of going after the same thing.
Super. Is additive printing a reversible process? Can you unprint it and reuse the raw material if needed? So
we're launching on the next Antares flight to the space station. We're launching a commercially sponsored polymer recycler that will take not only old 3D printed objects, but other waste plastics, and recycle that and turn that into 3D printer filament that then is compatible with our printers on the space station, creating this almost closed loop manufacturing and recycling environment.
Can your printer print a printer? There's a scary question.
Yeah. So not yet, but actually the very first object that we ever manufactured in space was a replacement cover for the very first printer to demonstrate that there is some inherent self-repairability quality to this technology, and also to show why this is something that we really went after, because it's a general manufacturing solution.
I, for one, welcome our robotic overlords. Do you see any benefits on adding humans in the loop now or later to increase quality assurance and quality control?
Our emphasis has been on actually trying to take humans out of the loop to try to make the systems more autonomous because of the high cost of having humans in the loop, both from a telerobotic perspective or from having them literally there in space. Certainly having people monitor those processes and ensure that they're operating is very, very important, but we think that autonomy ultimately will make these things more cost effective.
Wow, thank you. We are out of time, and despite the fact that the team keeps issuing questions, we're out of questions. Thank you very much.
Thank you so much.
Thank you.